All right. So this is the last seminar of my series. I'll be departing from Singapore on 31st of July. Okay. Has been such a pleasure to see all of you. Thank you for coming. And this is I didn't really expect this turnout. This is pretty good, pretty encouraging. We have a full room here. Okay. Um, so today we're going to talk about something difficult. Um, so if you think about the whole journey in joint theory so far, um, you know, we really have come a long way, right? So we started with cyclic queries, and then we moved on to cyclic queries. And for cyclic queries, the AGM bound is a worst case bound. So you've been told about that. I should have said, right? You've been told about that, but you should not get fully convinced. At least not yet. Okay, not after today's seminar. Why? Well, in order to convince you that the AGM bound is indeed the bound you should be looking at, I have to show you both sides. Okay, the upper bound side and also the lower bound side. Okay. So for the upper bound side, I did that already. Okay, I gave you this split theorem, if you still remember it. And the split theorem implies a super simple algorithm, I mean, at least conceptually, super simple algorithm that will allow you to process any join with a time complexity matching its AGM bound. Okay. So today we will close um, our discussion uh, by um, by uh, completing the puzzle with one final missing piece. Okay, so today I'm going to show you how to prove the tightness of the AGM bound. Okay, all right. Before I can commence talking about the proof, I'll have to fill you in on the fundamental, on some fundamental result I will need, okay, in my proof. Now, this is such a great excuse to talk about linear programming. Okay, LP for sure. Okay. Linear programming is super important. I'm sure, in the next few decades in your career, you will encounter linear programming multiple times. Um, Today, we will learn about something useful, something non-trivial about the mathematical nature of linear programming. Okay. Now, first of all, let me give you a very intuitive idea of what linear programming is, right? So to jumpstart, um, to jumpstart you, even if you had no experience before. Okay. So consider first two-dimensional space, right? So two-dimensional space, we have this x and y dimension, right? So you think about a linear constraint to be a so-called half plane. Okay, so what is a half plane? Half plane essentially says, okay, I have a line here. That's a linear. Okay, and this line naturally cuts the space into two halves, right? The upper half and the lower half, and then you specify one side of it. Okay, you say, okay, this is my first constraint. All right, my first constraint. I'm interested in the points or x, y, coordinates, right? Falling on this side of the plane. Okay, cool. And then so that's one constraint. Okay, and then you can throw in additional constraints. So remember, every constraint is not, I mean, these constraints, they are not lines. Every constraint is a half plane. Now remember that, right? It's specified by a line, but also you have to specify a side of the line, right? So say um, another constraint like this, okay? So linear programming, as you can see, right? So everything's about such kind of linear constraints, okay? So you can throw in a lot of constraints, and then you ask the question, what is the lowest point among all the points that satisfy all these constraints? All right, so this is actually a generic definition of linear programming in two-dimensional space. Okay, so as you can see in this case, if I have only 3 linear constraints for you, the answer to this question is unbounded, because you can move your point as, you can keep pushing your point down, right? And, I asked the question, right? What is the lowest point? Or phrased differently, I would say, what is the minimum y coordinate, of all those points satisfying all of these constraints, right? So you would say, okay, in this case, the solution is unbounded, right? Because it can go arbitrarily small, right? Unbounded. Okay, good. So this is one type of, optimal values you can have, or one. I would try to avoid using the word solution for reasons that will be clear later. But in terms of answer, in terms of output, in terms of the optimal value of this linear program, this is the first type, right? Unbounded. All right. Now, let me tell you another type, right? So what if I say, okay, now pay attention carefully. So if I say, okay, now I have another constraint here for you, the red one. Still the same question, okay? Among all the points satisfying all 4 constraints here, what would be the smallest y coordinate of those points, right? So in this case, the answer would be nothing. Okay, there's no optimal value. There's no output for this linear program. As you can see, right, the intersection area of all those half planes is empty. Correct? Okay, cool. Now this is the second type, right? And now let's think about this linear program. Okay, now this time you have a bounded optimal value, right? Now remember the question that I asked, right? What is the smallest y coordinate of those points satisfying all 4 linear constraints? Okay, so clearly, the answer would be this guy here. Okay, all right, good. Now this is about linear programming. Okay, as I said, this is actually a generic way to describe linear programming in two-dimensional space. Even though sometimes you would hear people say, you know what, let's look for the highest y coordinate, the highest point of all the points satisfying all these constraints, right? Or the leftmost or the rightmost, or even more general, you might hear people say, I give you an arbitrary direction. I want you to find me the farthest point along that direction among all the points satisfying all these constraints, right? Okay. However, I insist that the version that I gave in the beginning is general enough. Why? Because I don't really care what your optimization direction is. I can always rotate the coordinate system so that the optimization direction becomes the downward direction. You see what I'm saying? Okay. So we might as well just focus on the one that I mentioned earlier. Okay, is that all right? All right. So this is linear programming, okay? But this is a linear programming in two-dimensional space. If you understand the two-dimensional definition, and you can immediately extend the definition to arbitrary dimensionality. Okay, so for example, in three-dimensional space, we'll no longer have half plane. We'll have half space, right? So the boundary of this half space is not going to be a line anymore. It's going to be a three-dimensional plane. You see what I'm saying? All right. So the same notion of plane, I mean, this hyperplane notion extends very naturally to arbitrary dimensionality. Okay, you could have 10-dimensional, 20-dimensional, 50-dimensional, you know, um, and and uh, and every linear constraint becomes an inequality. You see what I mean? An inequality. Okay, so in this inequality, you will have as many variables as the number as the dimensionality, as the number of dimensions. For example, here you will have x and y. Okay, I will refrain from using x and y because, in three-dimensional space, I will be using x, y, z. In 10-dimensional space, I'll be using a lot of letters that way, right? So I will instead saying, x1, x2 to refer to the coordinates, right? So in general, if the dimensionality is d, let's say, and then you will have x1, x2, all the way to xd as the coordinates, and every linear constraint is going to be a linear inequality of these coordinates. Okay, is that cool? All right, very nice. So if you look at the two-dimensional space once more, if the optimal value of this linear program is, it exists, is non-empty, and then it's definitely a vertex in this polygon, which corresponds to the intersection of all these linear constraints. Now, this is a very, very useful way to think about linear programming geometry by resorting to geometry, okay, geometrically. Okay, so for example, in this case, if I say what is the intersection area of all of these linear constraints, then you will see this is the intersection area. Okay, so if I say, okay, what if I want to find the point with the smallest y coordinate, you can prove that the optimal value is always given by a vertex of this polygon. Bear in mind that this polygon could be unbounded. For example, if I remove the red constraint, and then the polygon is going to be all the way down, correct? Okay, but in any case, it will help a lot to remember that the optimal value of this linear program is always given by a vertex of the intersection area, which is always a polygon in two-dimensional space. In three-dimensional space, it's going to be a polytope. Okay, in four-dimensional space, 10-dimensional space is going to be a polytope, is what I mean. So here essentially gives another way to ask the same question, right? So in general, I give you a bunch of linear constraints. Those are half spaces, right? And you know that there's an intersection area of those half spaces, even if it's empty. And if it's non-empty, and then it must be a polytope, if you think about it. This is something you can prove inductively, right? You start with the whole space, and then you do one cut, another cut, etc., right? So you will see that the intersection area is always a polytope. So you know the polytope exists. Maybe it's very difficult to compute. It does exist, okay? And you can prove that, since we ask for the lowest point, right? Actually, it doesn't really matter which direction is your optimization direction. The point that gives you the optimal value, on that direction is always one of the vertices. And sometimes you could have ties. Maybe a vertex will be tying in score with some non-vertex point in the polytope. However, if you insist on just focusing on the vertices, you are able to do so. Is that okay? All right, there it is. Now let's look at the following formulation of linear programming. Okay, I'm going to write down this word primal here. At this point, it doesn't mean anything yet. Okay, I write it down here because it's going to be useful later, but for the time being, you can ignore it. Okay, now what if I say, well, I describe a linear program in the following matrix form. Okay, let's see if it makes sense to you. Okay, so I would say, A, this is an M by N matrix. Okay, and I also have another M by 1 matrix, so that's an M-dimensional vector. Okay, and here I have a vector. This is actually a point in my two-dimensional analogy. So this is an M by 1 vector. So this is basically the point inside this polygon. I will look for this point to do some optimization. And here, this is C is basically the optimization direction. Okay. So with these four matrices, and then I can describe this linear program as saying the following. want you to obey this inequality. Let's take a moment to understand this inequality. Okay, so first of all, let's understand the dimensions. Let's say A. So here, this is m by n, as I said, right? And this x, this is m by 1, correct? And this B, as defined earlier, this is m by 1, right? So in terms of dimensions, we seem to be fine. Okay, by the way, if you have, so what, I also have to explain a little bit what is less than or equal to mean, right? Because this is a vector comparison, right? So this vector comparison basically says, every component of the vector on the left will have to be less than or equal to the corresponding component of the vector on the right, right? So basically something like this, 1, 2, this is less than or equal to 2, 3, this is fine, okay? But if you say this 1, 2 is less than or equal to, say, 0, 3, and this is not fine. So you get the idea, right? This is a component-wise comparison, okay? So if you look at this linear program, you should get convinced that this is essentially describing a set of linear constraints or half spaces, if you will. You can see that, right? So if I say, okay, what are the variables? The variables are x1, x2, all the way to xd. Okay, so if you look at, if you want me to be very, very explicit, I can even tell you what are the inequalities. So see, this is A, right? M by n here, and this is x. Okay, so you can see every row of this matrix, gets multiplied with this vector, right? So that's going to give you something here, right? So this is the value standing on the right-hand side of the inequality. See what I'm saying? And you have how many inequalities? You have m inequalities. In other words, if I describe things like this, you can think about it as a linear program in n-dimensional space with how many constraints? With m constraints. Is that right? Okay. And I want you to maximize, this value. So remember, C is an n by 1. So the transpose becomes 1 by n. So essentially, this is the dot product between C and X, right? I'm not going to go into the details of this, but the dot product essentially says, I give you a direction, right? I want you to find me the point, that's farthest along this direction, okay, subject to the inequality that I described earlier. Okay, so this is just another way to describe any problem. Okay, is that all right? Okay, very nice. Now, something that is probably hard to believe if this is the first time you see the primal form. Okay, so I'm going to force another requirement. So this requirement says x will have to be larger than or equal to 0. Now, once again, this is a vector comparison. Okay, x is a multidimensional point, right? It has x coordinates, and on the right-hand side, this is, of course, a vector. So essentially, I am saying I'm just going to focus on the points in the first quadrant of this data space. You see what I'm saying? Okay, all right. So I argue that if you want to study linear programming, it suffices to study this form of linear programming. Clearly, this is sort of like a subset of all the linear programs you can have, right? However, I'm saying we're not losing any generality here. And why? Well, for the primal, I can give you the intuition. If you still remember the polygon analogy that I told you, the polygon, and also you have to remember that to solve a linear program optimally, essentially, everything boils down to looking for the best vertex in that direction, right, of a polygon. So imagine, I keep the polygon intact, but I'm going to move the polygon. I'm going to shift the polygon to the first quadrant. You see what I'm saying? And I should not be changing the nature of the problem. I will be changing the optimal value, but after you have got the optimal value of the new problem, you can always convert it back into the optimal value of the old problem. See what I'm saying? So that's the intuition. All right, good. All right, so enough with the intuition because what I said is not entirely precise. All right, but hopefully that will be enough for you to believe that this is not losing any generality. Okay, so that's the primal form. Okay, very nice. Now, something very important. I said I'm building. I'm going to present one very important theorem about linear programming, and this is something we're going to rely on to prove the tightness of AGM bound, right? So now, in order to introduce this theorem, whose name is strong duality theorem, I need to introduce the dual form. Okay, dual form. Okay, now watch carefully, please. If you have the primal form defined like that, okay, I can always define the corresponding dual form of this linear program on the left hand side. Okay, so this dual form can be stated very concisely. So this is A transpose. Okay, and this Y becomes an m-dimensional vector. Okay. Now, on the left-hand side, you can see the inequality directions are less than or equal to. Okay, and here it becomes larger than or equal to. Okay. Now, if you look at the matrix, right, let's go by dimension. This A transpose n by m, correct? And this y is m by 1. So if you do the matrix multiplication, you should get an m by 1 vector. You see what I'm saying? And on the right-hand side, you should have an m by 1 vector. And as I said, right, so this is the dual form of the primal form. So you must be looking for something that already exists in the primal form, right? And you're looking for a c-dimensional vector, right? So if you go along this line, there's no room for mistake, and this will have to be larger than or equal to c. Okay. All right, so now you see everything sort of like is the opposite of what was happening in the primal, right? So this inequality direction has changed. Now, finally, you also want to change the maximization to minimization. Okay, so this minimization, obviously, you will be dealing with y, but this will have to be the dot product between y and something, and you are looking for an m-dimensional vector. So there's only one vector that we haven't touched in the definition of the primal, and that will have to be b. Okay. So this is almost the dual form. Okay. Now, something that's really hard to believe. Now, this time, this is something far more complicated than just moving a polygon, but something that is difficult to explain in 1 minute is that this dual form for this dual form we can also introduce this additional constraint. Now, this is going to take a long story to explain. I'm not going to go into it. Okay, unfortunately, we don't. This is simple enough to understand, right? But you can go to the internet and look for the proof of this. Um, this is not the focus of today's seminar. Okay, and with this, now you have the complete dual form of the line. Okay, all right. Now the strong duality theorem says the following. Okay, in English words, if each one of them has an optimal value that is bounded, okay, if any one of them, the primal or dual, let's say the primal, has a bounded optimal value, okay, and then the other form, let's say the dual, also has a bounded optimal value, okay. In other words, it's not possible. Like on the left hand side, you got empty. On the right hand side, you have something bounded. That's not possible. Okay. So that's the first bullet. The second bullet of the theorem says that these two optimal values will definitely be the same. Okay. All right. So let's write it down. Okay. So primal bounded optimal in terms of optimal value, right? So once again, the optimal value says, what is the optimal value of this objective function, right? Okay, so this is bounded if and only if the dual has the same optimal. So this is the strong duality theorem. Okay. Now this is um, the mathematical theorem that I need in order to prove the tightness of the AGM band today. All right. Okay. So let me try to solicit some questions from you. Do you have any questions about the theorem that I just presented? Okay. So while you are brewing your question, let me just point out why we need to have the primal form and the dual form, and why is that necessary, right? Why is that even useful? Okay. So in mathematics, the more perspectives we have, we can hold on the same thing, the better. The better. Okay, because you basically intuitively you know that you're looking at the same optimal value, but sometimes it will be easier to approach this optimal value easier from the primal perspective, but sometimes it could be the opposite. Okay, and in any case, you don't lose anything because if it turns out the other perspective is useless, you just ignore it, right? But what if it turns out to be useful? And I mean, by now you should have this experience that the same thing. And if you are able to change perspective, and sometimes you might get surprised. Okay, and sometimes the problem can get a lot easier. All right, so if you have taken this course, computational geometry, you might have this point plane duality. You might have learned about this point plane duality, and that, for example, right? So let's say the linear constraints, they have a lot to do with convex hull, if you know what I'm talking about, right? The same thing, but if you can approach it from different perspectives, and sometimes you could, find additional properties to help you with. All right, so that is the primal and that is the dual. We'll come back to this form later, but this is what I'm going to need today. Okay? All right, cool. Very nice. Now, next, I'm going to present to you the statement about the tightness of the AGM band. Okay, and then I'm going to prove it. Okay, so we have a joint. So today I'm not going to rebuild the notation system. Okay, so I will simply say a joint schema like this. Okay, so this joint schema, so this V, this is the set of attributes that exist in the class of joints under this schema, if you understand what I'm saying, right? So, for example, I could say A, B, and C, and this is going to be the example I'm going to use. A, B, and C, I specify the attributes here. Okay. And this Y indicates the schemas of the relations of the class of joints you are interested in. Okay, now what do I mean by schema? Every relation, its schema is defined as the set of attributes inside the relation. Okay, so in my running example, I'm going to use AB, AC, and BC. Okay, so this is the triangle joint we have discussed multiple times. Okay, so if I say AB, AC, and BC, you should not think about them as concrete relations. You should think about them as the schemas of relations. You see what I'm saying? In other words, I am really, really just defining a class of joints here, a set of joints here. So all those joints should have three relations. Okay, and the schemas of those three relations should be A, B, A, C, and BC respectively. Okay, is that all right? Good, very nice. Now, very importantly, I'm going to give you this so-called cardinality vector. So this is a vector over the schemas. Essentially, I'm saying, I will constrain how many tuples you can have in each relation. Okay, So in my running example, I'm going to give you NAB. So these are three integers, NAC and MBC. Okay, so this is the cardinality vector. Okay, all right, good. And then I claim that definitely there is a relation such that this relation will produce a lot of tuples in the joint result. Okay, and the number matches the AGM bound that is defined using N. Okay, so this is what's coming your way. All right, now let's define this AGM bound carefully. Okay, so if this AGM bound, if this N is already fixed, and then what is AGM bound? So AGM bound is essentially saying, you look at the you look at the following expression. So this expression says, okay, this expression says, you know what? I will use my running example to help you recall what an AGM bound is. Okay, so this says NAB, okay, to the power of WAB. I'm going to explain this W very shortly. This N, AC, WAC, and BC, WBC. Okay. All right. So some of you should already recognize what I'm talking about, right? So now what is this W? W is a so-called fractional edge cover of this schema graph, right? So this W satisfies the following: WAB plus WBAC. This will have to be at least one. You can think about it as, WAB is the weight that you want to put on the edge AB, and WAC is the weight on AC. And therefore, if you look at the sum of the left-hand side, so that is the total weight on vertex A. You see what I'm saying? Okay. So it will have to be at least one. So this WAC plus WBC will also have to be at least one. And then finally, we have one more inequality. All right. Is that okay? Okay, good. So I'm not going to write down the generic form of this inequality, but you should know that, this, I mean, by now, right? I want to save some time today, but we have talked about this many, many times in the previous seminars, right? What the AGM bound is, or the fractional edge cover is, okay? So today, I will get the full details for my running example, but hopefully you are able to recall what an AGM bound is. Okay, if not, you have to resort to my previous seminars. Okay, good. So now, if you look at this W, um, um, so this W has a lot of freedom. Okay, you can choose any W, and any W once again is called a fractional edge cover, right? So you can consider all the fractional edge covers of the schema graph G. Okay, which is just a triangle here. And among all of them, you want to minimize this objective here. Okay, and the minimum value of that objective is referred to as the AGM bound. Okay, AGM bound. And this AGM bound is defined using this cardinality vector. Now, the claim is that I can always find you relations. Let's call them RAB, RAC, and RBC. Okay, so if you give me the cardinality vectors, feel free to give me any cardinality vectors, NAB, NAC, NBC. Okay, so as long as there are at least one. All right, I can always find you relations satisfying the following. Okay, their cardinality is exactly as specified in your vector. Okay, RBC, so this is exactly NBC, and finally, RAB is exactly NAB. All right. Okay. And furthermore, if you look at the join, okay, so let's say Q is the join defined by these three relations, and then the join size of Q is larger than or equal to the AGM bound I just defined over some constant. And you will see for this particular query, the constant will be 8. Okay, well, A may not be the tightest. I mean, A will be the constant that I can prove today, in the next 30 minutes. Okay, but let's look at the statement again, right? So the statement says the AGM bound is the best upper bound that you can come up with on the joint size up to a constant factor, provided that the only information that you use is the cardinality values. Okay. All right, so I'm going to pause a little bit here to see if you have any questions or any doubts about the statement here. Okay. Well, I have to point out that this statement is not saying that every relation whose cardinalities are described by NAB, NAC, and NBC will necessarily produce a joint result matching the AGM bound. This is not what the statement is saying. And clearly, this is not true, right? Because you could have 3 relations, and those relations have, arbitrarily irrelevant values. So the joint result is going to be empty for sure. Okay. But if you have been with me, all this time, you know that one correct way to study the joint problem is to say, okay, if we use the cardinality values as the parameters to gauge the efficiency of an algorithm, what is the best bound we can claim? You see what I'm saying? And this statement aims to answer that question. All right, so the statement says, well, the AGM bound is the best claim you can produce using the cardinality values. Why? Because with any set of cardinality values, if that's the cardinality vector here, right? So with any vector, I can always give you a joint that conforms to the cardinality values that you just specified. And this joint will produce as many tuples in the result as the AGM bound, up to just a constant factor. And you know that no matter how smart you are, you need at least constant time to indicate something that you have a result, you have a tuple in the result. And therefore, no matter how smart you are, the running time of any joint algorithm will have to reach the AGM bound, omega of AGM bound, up to a constant factor, right? And therefore, this makes our algorithm with the spread theorem in the previous seminar worst case optimal, up to just a small factor, polylogarithmic factor, right? So this is how the dots get connected in the story. You see what I'm saying? Okay, good. Now this is what I'm going to prove. Okay, so this is what I'm going to prove today with this triangle joint. Okay, so remember this is seminar. This is not a PhD course. In the PhD course, I will give the whole proof. Actually, the whole proof is in my lecture notes. Okay, however, clearly it will be a lot easier to give you the main ideas using a concrete example. And once you understand the proof on this concrete example, it will be much easier for you to understand my proof in the notes. Okay, all right, good. So if you are ready, let's get started. Okay, all right, nice. Now I can say, let's focus on the following optimization problem. Well, as you can see, this is, I forgot to say all the weight values will have to be non-negative. I forgot to say WAB will have to be larger than or equal to 0. WBC and WAC, they will have to be larger than or equal to 0. Now, remember, this is fractional edge cover, right? Although I did say it in previous seminars, so I should also have the condition like this, right? Good. So if you look at this optimization problem, it's not a linear program yet. Okay, you can look at the constraints, that's fine. All the constraints are linear, no problem. You do have a polygon, okay? You do have a polygon, okay? By the way, you can see that this is a minimization problem, right? Let me emphasize here, this is a minimization problem, okay? So you can see that this problem definitely has a bounded value, right? It would be stupid to say, oh, the minimum is infinity, right? Because you can clearly construct a W that will give you a finite value, right, for the objective function, right? So this uh, optimization problem has a bounded, let's say, optimal value. Okay. However, this is not a linear program yet because in the linear program, the objective function will also have to be linear, right? It has to be the dot product between this W and something else, right? However, as you can see, instead of minimizing the product, you could instead, minimize the log of it. Okay, and therefore you could say, well, the problem, is essentially the same as minimizing the following linear objective function. Okay, so I want to remind you what are the variables in this linear program. Okay, so the W the W represents the vector that you try to choose. Okay, and remember this n vector, right? NAB, NAC, NBC. They are the vectors that you give me in the first place, right? So I'm not choosy over the n vector at all. You give me whatever vectors, and it's my job to convince you that I can indeed match the AGM bound of that n vector using concrete relations. I have to construct the relations for you. Okay. Now, indeed, we have a linear. Okay. Look at this form, right? So let's remember this is a minimization here, and also this is larger than or equal to here. Okay, so I want to test you a little bit. This linear program is the primal form or the dual form. Okay, it's the dual form. All right, look, we got minimization here. Okay, we got minimization, right? In the primal form, we have maximization, and also, everything checks through, right? Because this is larger than or equal to, and indeed we have larger than or equal to here. Okay, and you will see this is one of those scenarios where this two perspective approach, helps. Okay, and if we try to reason with this AGM bound directly in the dual form, and then I would say it would be pretty hard to construct a hard instance, a hard joint to match the AGM bound. However, once we get to the primal form, everything, is going to work out much more easily. Okay. Now let's write everything into this AY form, that we needed in the dual format. Okay. So let's look at the following matrix. I'm giving you the matrix form of precisely this linear program in the green box. Okay, so I'm not really doing anything fancy here. Okay, so let's say I got AB, AC, and BC here. Okay, and I have this vector W, right? But instead of calling it W, I'm going to call it Y because I used Y in the dual definition in my introduction to LP, right? Okay, so this matrix is A transpose. Okay, just to be consistent with what I had in the dual form, right? But you can call it AV1, okay? But this is a 3x3 matrix here. Okay, so this 3x3 matrix, I want to be able to capture the inequalities, right? So I'll be using larger or equal to something, and the right hand side I got 1, 1, 1 here. But then let's fill in the values of the matrix. Okay, so in order to capture this inequality, what do I need? I need to put 1 here, 1 here, and 0 here. Okay, see if you get convinced, right? So this Y has 3 components, right? YAB, YAC, and YBC, right? They're just, the W vector, correct? All right, so if I put 1, 1, 0 here, and then you get the first inequality, right? So now immediately you can see there's a clear pattern here. The pattern is that you want to put one here simply because B as the attribute is inside the schema, is inside the edge AB, which is the column there, right? So you put 1, 0, 1, and then 0, 1, 1 to complete the matrix. Okay, and furthermore, you have this y larger or equal to 0, and you want to minimize what? You want to minimize this C. You want to minimize this, what's the symbol that I use? B, okay. So you want to minimize B transpose Y, okay, where B is, this vector. Okay, so instead of looking at the linear program in the green box, we could instead look at the matrix form that I just wrote down. Is that okay? All right, so I'm not doing anything fancy yet. This is just another way to present the same linear program. All right, so maybe one thing that could confuse you is this renaming here. Instead of calling it W, I call it Y, right? I hope that's okay, right? So if I say YAB, I hope you understand what I'm saying, right? YAB, right? So you remember Y is a three-dimensional space, and what are the dimensions here? The dimensions are AB, AC, and BC. Is that okay? All right, cool. Very nice. Okay, all right. So I'm going to copy this to the next page, right? So that you get a cleaner canvas. All right. Okay, now we're going to work on this. Okay, we're going to work on this. So as I explained, this LP, in terms of optimal value, right? Optimal value, here, right? Optimal value. As I said, this will have to be bounded. Okay, I'm not going to fully explain it, but as I said, first of all, this cannot be empty, all right? Because you are able to find y to satisfy all those constraints, right? Clearly, and second, cannot be unbounded. I so I don't have time to go into the details of that, but this should be quite easy for you to verify. Okay, so this is the bounded. This is the bounded category. Okay. So why is this so important? Because if this is bounded, and then we know we can have a dual view, right? So we can apply the strong duality theorem to look at what happens in the primal form. This is the dual. Okay. All right. Now, before I go there, I'm gonna write down this y star because it's bounded, right? Definitely there is an optimal solution. By the way, y is referred to as a solution to this LP, right? So think about that's a point inside the polytope. That's a solution, right? So among all the solutions, so solution basically means it's a feasible, right? So it's a feasible point that will make all the inequalities satisfied, right? So it's a solution to the inequality set. And the best solution, this y star, is the solution that will give you the optimal value of the linear programs, all right? So that's y star. Is that okay? Okay, good. Now let's write down the primal form. Okay, so primal. Now this is dual and the primal. So let's start with the matrix, right? So the matrix says transpose. Okay, so in the dual, it's AB, AC, BC, and therefore I will have AC, AB, AC, and BC as the rows, and also ABC as the columns. Okay, so let me quickly write down the values as well. Okay, so this is just the transpose of the matrix in the dual form, right? Which one is AT, which one's A? Doesn't really matter. Is that okay? All right, good. Now I'm going to write down this X here. Now this time this X, although, in terms of dimensionality, it also happens to be 3. In general, it's the size of V, right? The number of attributes you can have. But, in this particular example, it happens to be 3. But you have to understand that this X is no longer in the same space as the vector Y, right? So vector Y is in the space of AB, AC, and BC. So that's basically the edge space. So in general, this Y has the dimensionality that equals the number of relations you have in the schema, okay? And this the X has the dimensionality equal to the number of attributes you can have in the schema, okay? So in this case, it turns out to be 3, but you need to understand they are in different spaces. Okay, cool. So this X, and then I have every right to say XA, XB, and XC later. No problem with that, right? Good. So let's write down the inequality. The inequality definitely should be less than or equal to. Okay? And then I should be looking for something that's defined in the ABC space. Sorry, I misspoke. I misspoke. I'm looking for something that's defined in the edge space, AB, AC, and BC. Why? Because look at it, right? So every row in the primal form should give you an inequality, right? So you will need some value. You need one value for every row. Okay. All right. So, well, of course, you can always try to do the matching, in the primal and dual, right? But once you um, remember the words that I said, right? So in this case, you should be looking for something that's defined over AB, AC, and BC. I mean, there's no room for mistake, right? So there's only one thing you can put here, and it will have to be log A N A B. So that's the B here, by the way. Okay, the B will have to be on the right-hand side, right? So if you don't believe me, look at my notes, right? So that's exactly what I said, right? So this is log N AC, and this is log BC. Okay, good. Now this time you have to do maximization, right? Everything is reversed, right? Maximization of Y, and then this is C transpose. So what I'm X, not Y. Sorry, transpose. Okay, so what is C? C is here. This is C. Okay, so transpose C. Look at C. C is so special, right? All the components are one, right? So this is essentially just XA plus XB and plus XC. Okay, so this is the primal one. Okay, so immediately I can say that the primal form has a bounded optimal value, and therefore I can define this X star as an optimal solution, an arbitrary optimal solution. Now remember, optimal solution is a solution of the linear program that defines the optimal value. Is that okay? All right, good. Now, by the power of strong duality theorem, what do we know about this X star and Y star? You know that these two optimal values are exactly the same. And therefore, I have what? I have X star A plus X star B plus X star C is exactly what? Exactly this thing that I'm going to write down. It's going to take a while. Y star AB plus log NAC, Y star AC, and then plus log NBC, Y star BC. Okay, so this is from a strong duality theorem. So far, so good, right? Now this is an equation I'm going to need later. Good, very good. Okay, now I'm going to proceed to construct my relation. You remember the goal of the business here, right? Still, can you still tell the story? The story is you give me arbitrary NAB, NAC, and NBC. My job is to provide you with three relations. All right, they will have to match the cardinality values you provided. And furthermore, my construction must be bad for the join in the sense that, this join with these three relations will have to produce a lot of tuples. In fact, so many that the number of tuples will have to match the AGM bound defined by your n vector. Okay, so that's actually a daunting task if you think about it, right? However, now I can give you the relations right away. Okay, all right. So you see, I have x star there. I take this x star. I can take an arbitrary x star. I'm not worried because any x star would have to satisfy this equation here. Okay. All right. Um, just a little test. Okay, so this y star. What's the relationship between y star and the optimal fractional edge cover, or the AGM bound of your schema graph? You know, in order to define the AGM bound, you need the best fractional edge cover, right? So that's W, right? So let's call that W star. So what's the relationship between y star and W star? Same. All right. So y star is y is just W. I just renamed it. You see what I mean? Okay. So that's how things get connected. Okay. All right. Good. Now, just to give you a heads up message, right? Look at this equation, right? So if I raise both sides of the equation to the power of 2, right? To the power of the left-hand side, to the power of right-hand side, what do you get? Well, on the right-hand side, you should see you are getting the AGM bound already. All right, so this is what will be coming your way later. Okay. All right, good. Enough with the heads up message. Now here is the construction. So you see X, I emphasize X is in the vector, in the attribute space. ABC, right? So I get to say XA, XB, and XC. Okay, good. Now I'm going to define the domains of each attribute. Domain, you see what I'm saying? Domain, this is the set of values I will use to construct the tuples. So domain of this attribute A is simply the set of integers 1, 2, all the way to 2 to the power of X star of A. X star. So let me give you some time to take this in, right? So X star. So that's the optimal. That's an optimal solution to the primal on the right hand side, right? Okay, so 2 to the power of that. But some of you will protest. Some of you will say, "Hey, that doesn't make any sense, right? Because you said this is the set of integers, right? But 2 to the power of X star A may not be an integer because it could be a fractional value, right? And that's why instead of saying X star A immediately, I will use a floor here. So basically, this is why I get this constant A, the AGM divided by A. So I do a little bit of relaxation here, as you will see. Okay, good. All right, so this is the domain of attribute A. Okay, only the domain. Okay, I haven't constructed any tuples yet. Okay, but I have told you, the set of A values possible, right? In the same way, I will also construct the domain of B, domain of C. Okay, good. So if you think about this, everything looks quite elegant, right? So you have more and more reasons to believe that this is leading to something promising. Okay, it's quite elegant, right? Very nice. Okay. All right, now it's time to give you RAB. I have to construct 3 relations, right? Now this is the first one. RAB is very simple. You look at the domain of A, look at the domain of B. I will take the Cartesian product. Well, this makes a lot of sense because I want to achieve the effect that for any small a from the domain of A, small b from domain of B, there is something for the combination. You see what I'd say? So this is, in retrospect, not surprising, right? Because I want to sort of generate a lot of results, and Cartesian product is the way to go. So this is precisely the domain of A, Cartesian product with the domain of B. Okay. By the way, RAC, well, you can guess already. So that's another Cartesian product, right? Domain of A and domain of C. But I will go there later. Now is a great time to discuss the size of RAB. Okay, what is size of RAB? Well, let's see. The size of RAB, I have a constraint on myself. because I said this relation must have exactly the size of NAB. You see what I'm saying? You gave me this NAB to start with. I promise that I will give you a relation with exactly that size. Okay, now let's see if I can keep my promise. Right? So what's the size of RAB? Well, let's take it slow. So this is precisely 2 to the power of the domain size of A. Now remember the floor, right? Times 2 to the domain size of, I'm sorry, it's the product of the domain sizes of A and B, right? Given by this expression. Well, you can see now I will ignore the floor, then I get 2 to the power of x star A plus x star B. Correct? Okay, good. All right. Well, now let's look at the inequality here. Okay. You know x will have to conform to the LP, and therefore it has to obey the first inequality, right? So you see, I'm indicating the inequality for you, right? So this says the sum of A and B, the sum of XA and XB, right, will have to be bounded by what I have here, right? So this is bounded by 2 to the power of log of NAB. By the way, all the base, all the logarithm bases are 2 here, okay? So this is precisely NAB. All right, so I'm almost there. Well, the good news is that, I have constructed a relation, and this relation's size does not exceed NAB. Okay, so this is promising, but because if it exceeds, there's nothing I can do about it. And then I'm wrong already. However, there's still this last mile I have to conquer, right? So I promised a relation with exactly NAB tuples, but now it could be less than that, right? Because I took the floor, right? Well, easy. You just append dummy tuples, rubbish tuples there just to make sure that the size is NAB, right? So the values will be from another world. You see what I'm saying? You would take rubbish values that are outside these 3 domains. Okay, so they are simply, the placeholders. Is that all right? So that's AB. Okay, that's AB. Good. All right, so now you should get convinced that I can construct RAB. All right, good. Now I'm going to construct RBC and RAC in the same way. Okay, so this is called the product database if you look at the theory. Okay. All right, cool. So now these 3 relations, their cardinalities, they are bounded by the sizes that you specify, right? Bounded, right? So when I say bounded, I actually imply equivalent, right? So if you want, you can make it equivalent, right? But I don't even need to fill up the quotas in other way, right? Okay, good. Not in other words, okay. Now let's look at the join. All right, so what is the size of the join, right? So let's analyze the join of this query, of this join, the size of this join that I just constructed with these 3 relations, right? Now you think about every small a, small b, and small c, right? Small a from the domain A, small b from the domain of B, and small c from the domain of C, right? You see, you take an arbitrary member of the Cartesian product of the 3 domains, right? Small a, small b, small c. I claim that this will have to be in the join. You see what I'm saying? Okay, I don't even care about the join tuples that could be produced by the dummy values that you appended into the relations. I don't even count those tuples because I won't need those tuples, right? All right. So I claim that this small a, small b, small c is definitely in the join. Okay. So for this purpose, it suffices to check the projections. You see what I mean? So I'm going to check, okay, is AB in the relation RAB I constructed? Well, the answer is obviously yes, because that's exactly how I constructed this relation AB, right? How about this A and C? Are this tuple AC, is it in the RAC? And this BC, is it in the RBC, right? So the answer is clearly yes. And therefore, I can claim that the size of the joint is at least how much, right? So this will be the product of the domain sizes of the three attributes I constructed, right? So it will be X, floor X star A plus floor X star B plus floor X star C. I hate floor. I really hate floor. Why? Because, if it's a floor, I cannot really use XA plus XB plus XC. But the equation says it's the sum, right? Not the floor, right? That matters, right? So I'm going to do something simple, right? So in general, right? So if you have something like this is strictly larger than t minus 1. That's what I'm saying. So 2 to the power of this strictly larger than 2 to the power of t minus 1. So this is simply 2 to the t divided by 2. Correct? So that's how I got this 8. You see what I mean? So now I will forget about the floors. Now I have divided by 8. Correct? Very nice. Now, still remember the heads up message that I gave you, right? Now this is coming your way now, right? So now I can use the equation from the strong duality theorem to tell me, this is really just the right-hand side of 2 to the power of log of a long expression. Now, what is this expression? Well, let's do it. So this is NAB to the power of y star AB times, okay, times, all right, NAC to the power of y star AC times NBC to the power of y star BC, okay, divided by A. All right, so now I believe this is something everybody can see. This is AGM N divided by A, as desired. All right. All right, thank you very much. This is the end of my seminar.